Welcome. Today we are going to start with a topic of circular and dual polarized microstrip antenna. As we know, it is one of the main advantage of microstrip antenna that using a single patch you can realize multiple frequency design, or you can realize single or dual polarization and thus a circular polarized design. So we are going to see today that how a circular polarized antennas are designed, and then by modifying CP designs or circular polarized designs, how a dual polarized configurations are achieved. Now in this topic we are going to cover following things. First, we will talk about the necessity of circular polarized or dual polarized microstrip antenna. Then we will talk about different techniques that realizes CP MSAs as well as DP MSAs. I am referring to this as a short form. CP stands for circular polarized, DP stands for dual polarized designs. Now there are many techniques which are evolved over the last 3-4 decades. Okay, so the earlier ones which were introduced was single and dual feed designs for realizing circular polarized designs. Okay, they were using power divider circuits also that actually creates orthogonal modes. Then using a single feed, the designs of slot cut MSAs were used to realize CP. Now the role of slot here in realizing CP designs are little bit different to the role of slot in talking about compact antenna design, which we have seen earlier, or a wideband antenna design. A slot basically supports the generation of CP by ensuring dual orthogonal modes. So the role of slot here is different. The dimensions of the slot and their positions are also much different as compared to their case in the compact design as well as broadband design. Further, another technique, because slot is cut in the patch, we can place stub on the patch edges which are orthogonal, okay, and that realizes a circular polarized conditions. Another technique is the use of modified patch shapes. Don't use slot, don't use power divider circuit, but by using a modified shape of the patch geometry, you can create orthogonal modes. Of course, here the knowledge of field position, the resonant modes of that patch is essential. So by selecting those modified patch shapes, you can design a circular polarized antenna using a single field. So there is no need to have a power divider circuit or no need to have a slot also. Another very important or very convincing technique is to realize a CP design using resonant slots. We have seen in the past wideband antennas are designed using resonant slots. The same concept of resonant slot but with a modified approach is used to realize a circular polarized condition using a resonant slot. Okay, so here you are going to consider a U-shaped patch or a E-shaped patch. We will discuss those in detail in the due course of time. Then the last one is the modified ground plane technique to realize a circular polarization. So there are actually n number of techniques which are there. We will discuss and compare all of those techniques. Now, first, before starting with how CP is realized, what is exactly a circular polarization, what is a dual polarization, first we will talk about the necessity of circular and dual polarized microstrip antenna. What is the necessity? Now the thing is, polarization means what? When a signal is transmitted from a transmitter, say suppose my antenna is vertical, naturally a signal which is transmitted from the antenna is going to be vertically polarized or linear polarized. If I use a simple diode or a simple dipole, then the polarization of the antenna remains vertical. Now as we know, especially in all our GSM, Wi-Fi band applications or anything above 500 MHz, there is a line of sight communication which takes place between the transmitter and the receiver. In that process, the signal undergoes multiple paths. Due to that multiple paths, the reflections also signal come across, and whenever there is a reflection from any object, there is bound to be change of direction of the re-radiated electric field. So once a signal which is transmitted from a transmitter, you cannot guarantee that at the receiver you will get effective vertical polarized signal. That may have gone across different changes and the polarization would have become something different. Now if your receiver is only sensitive to vertical polarized antenna, why? Because my transmitter is vertical polarized, then you will have a signal loss, because we know the output received signal is proportional to the dot product of these two vectors. So it is going to be incident wave AI into the polarization of the antenna. So it is basically a dot product. And if the vectors are not matched, if the vectors are at some angle, or if the vectors are orthogonal means perpendicular, like this, then naturally the dot product will result into a zero or minimum component. Because what is dot product? It is the magnitude of 2 and the cosine of the angle between the two vectors. So if that angle is more, that means the vectors are misaligned, you will get a signal loss. Now to overcome this, I should have an antenna at the transmitter which can receive any polarization. Okay, which can receive any polarization, and because of that it can receive signal from the horizontal wave also, which is incident, which is supposed to be coming from the transmitter antenna, or it can be received in the orthogonal direction, which have gone across. Why orthogonal? Because the signal must have gone across multiple path propagation effects where a polarization of the wave is changed. So there is a necessity to actually design a circular polarized antenna at a receiver, so that independent of what is the multipath propagation effects are there, okay, so you will get a received signal which is not disturbed in any sense. So that's why a circular polarized antennas are preferred. Okay, now before going further, we will now, before actually discussing these techniques, we will little bit further go into the details of this polarization concept. We will try to correlate this with the radiation pattern, a cross polarization content, and then we will talk about these techniques. Okay, so now we will talk about what is exactly polarization, what are the different types of polarization, and by looking at the surface current distribution of the antenna, how the polarization of the transmitted wave can be judged. Now, polarization. What is the definition of polarization? It is basically the locus traced by the tip of the electric field vector with respect to time. Okay, so here one has to remember the moment, or rather the motion of the wave with respect to time and space. Now, by analyzing this with respect to time and space, to see the polarization, you can freeze one of the parameters. So what we are doing, I am freezing space, so I am observing the variation of the tip of the electric field vector with respect to time. So if at a given space point, if the tip of the electric field vector traces a locus which is a straight line, that straight line can be in any direction. Okay, that straight line can be this way also, can be this way. But over the time, at a given space point, the tip of the electric field vector traces a straight line. Okay, it may be like this, it may be like this. Then this is the condition for linear polarized antenna. Okay, this is the condition for linear polarized antenna. If tip of the electric field vector, okay, if tip of the electric field vector with respect to time traces a ellipse. Okay, that ellipse can be an angle at any direction down. Okay, that is the ellipse angle what we talk about. That ellipse can be aligned at any angle tau, or it can be an ellipse with angle tau equal to 0 also. Okay. So if the tip of the electric field vector with respect to time traces the locus of the ellipse, we refer to this as the elliptical polarization. Okay, this is the elliptical polarization. And then naturally you will see the amplitude of the signal vector are unequal in two orthogonal planes. Okay, whereas there is no orthogonal vector involved in the linear polarized design. So here, if you have a unidirectional signal, okay, incident onto the antenna, and if the polarization of the receiver antenna, suppose it is like this or like this, if it doesn't matches with the vertical wave which is incident onto the receiver, then you will get a signal loss, right? So there is a high probability that because of the polarization mismatch, because see, I am saying transmitter is like this, but the incident wave is coming like this, or it is coming at some angle. So because of that, the two vectors, the polarization vectors are not matched, and because of that you will get a signal loss over here. Now that signal loss can be minimized if I am using a elliptical polarized antenna. Why? Because this tells you the distribution with respect to space at a given time. So if the tip, as the tip of the electric field vector is tracing a locus of ellipse, it is elliptical polarization. Angle tau can be anything that depends upon the orthogonal components of the radiated field. But now, in this case, suppose the incident vector is coming like this. Earlier case, if the vector antenna polarization was like this, naturally you will get signal. But if antenna polarization is like this, there is going to be a signal loss. Here, if the antenna polarization incident wave polarization is vertical, then depending upon this vertical magnitude, your signal will be received. Okay? Whereas if the antenna polarizes horizontal wave is incident, then depending upon this magnitude of the ellipse, you will receive the signal. So in either of the case, your signal is not lost. It may be minimized in some angle, okay, depending upon what is the ellipse angle and the two axes of ellipse, what are their magnitudes. But in different angles means what? Mismatch of the incident polarization against the antenna polarization. So in different angles, you will not come across a situation where a signal is completely lost. Okay, so elliptical polarization, I say it's better if I have a multipath propagation effect. Now the best possible match over here will be obtained in a circular polarized design, because see what happens is, depending upon your ellipse angle tau, your vector shape will be different. Your component of the electric field magnitude in EY and EX will be different depending upon what is your angle tau. But if you go now to a circular polarized design, in circular polarized design, let it be angle tau be anything. In all the cases, the orthogonal EX and EY are going to be equal. Okay, since it is a circle, and hence you will not have any kind of signal loss over here. Okay.